Hello students, I wanted to talk to you today about the complex number field. You learned about what homomorphisms and isomorphisms are last week, and that was to try to connect the fact that we can treat the set of real numbers when we have those Cartesian products of real numbers here with component-wise addition and that special little star and circle operation. This is going to be an isomorphism to a field of complex numbers, which is going to include the imaginary value, that square root of -1. So all of these properties of a field now are going to be inherited as a result, and this a plus bi form that you see right here, you see that when it says a plus bi on that field, that's going to be a complex number form, where a is representing a real number form, b is simply a coefficient of that imaginary value of the square root of -1. And the inverse values are going to be found by taking a over a squared plus b squared plus negative b over a squared plus b squared times I. Okay, so you have that in there. But again, the important takeaway is that anytime you see complex numbers, it's the dead giveaway is that it's in the form of a plus bi. And so maybe it looks like something like 5 plus 7i, I'm just making up numbers here, or 2 minus 3i, which of course now the b portion of that, you'd say it's -3, not 3. Okay, so whenever we're talking about the complex field of numbers, we're going to denote it with that fancy double struck C, just like we had said real numbers, before. So when I say, hey, the real numbers with I included, we're going to call those the complex numbers. So there's a little bit of a history lesson in here where it talks about just kind of the progression of the mathematical understanding of these real numbers and on into imaginary numbers over time, and how historians first encountered those. Those of you that are really into your math history could probably make a note of this Diophantus, because anytime somebody refers to Diophantine equations, we're talking about equations where the integers must be integers only. So if you ever hear that term bandied about, Diophantine equations refers to equations that are only integer solutions. So just thought I'd throw that in there. They talk a little bit more about the history. I'll let you read this on your own. You don't need me to tell you about these various math historians and their encounters with the square root of -1. You can, again, like I said, you can read all through this on your own. So I wanted to skip ahead though and talk about the terminologies you'll see. So when you see this a plus bi for this, this is equals z. Z is going to be just the shorthand here, for this one I'm saying z is, a plus bi. If I'm talking about, if I talk about z, this a plus bi is going to just be, that's what the z is shorthand for. And if we throw a bar over z, if I say z bar, I'm talking about the complex conjugate. That is to say, so if z is equal to a plus bi, z bar is going to be the value of a minus bi, like so. So if I was in class here today, I would give you several different examples. For instance, if I said, okay, if z is 2 plus 5i, tell me what z bar is. If z equals -3 plus 2i, now what's z bar? And yeah, I would have just encouraged you to answer questions on these. 5 minus 6i, I've got, let's say I had 7 plus 9i. What if we had -5 minus 2i? So if I gave you those 5 examples here, what would you identify as the value of z bar? So I think you would probably, hopefully, come up with 2 minus 5i, -3 minus 2i, 4 plus 6i, hopefully you said. How about 7 minus 9i? And, oops, yeah, try -5 plus 2i, like so. All right, and some other operations I want you to work on today. I introduced a little bit last week, but I will talk a little bit more here. When we talk about conjugates, whenever I take some imaginary numeral such as 5 minus 2i, if I multiply it by its conjugate, one of the properties that you'll see down here is that when I take that product of an imaginary or complex number times its conjugate, you're always going to get a real number solution. Check it out. When I take 5 times 5, of course, we know that's 25. And then, of course, I'd get plus 10i minus 10i when I do the inside ones. And then finally, the last terms could be negative 4i squared. And, of course, we know that I squared is, in fact, negative 1. All right, so I have negative 4 times negative 1. This is going to wind up being plus 4 here. Meantime, this plus 10i minus 10i, all this is going to cancel out, leaving me with just 25 plus 4. Thus, the product of this was, in fact, 29, like so. And, yeah. Now, again, this list of properties of complex conjugates that you see on the screen right here, if you look carefully on these, you'll notice that these first 7 properties right here, you're going to find that these are going to be covered on the next pages here. Give me 1 second. There we go. Froze up for a sec. Exercise 293 is the proof of property number 1. Showing how we can, the conjugate of a sum of z plus w is the same as the individual conjugates added together. And then there's this law of the products. If I've got the conjugate of two different imaginary values, and those values are going to be a plus bi and c plus di respectively, I'll get ac minus bd minus ad plus bc times root I. Does this sound familiar? Yeah, it should. This is the this was that star and circle operation we encountered last week. If I take a conjugate of a conjugate, it should just take me right back to the original value, of course. And yeah, and you're just filling these in on these exercises here for 296, 297. Just again, I won't belabor the point on these. The answers are just in the document that I have for today, and obviously I'm just scrolling through these on the video. And that's going to take you through exercise 299, at which point you say, well, that was pretty easy. Indeed it was. All I'm asking you to do today is go ahead and fill those exercises in, and then go ahead and check out the IXL Pre-Calculus Skills R2 through R3. I'll leave you alone for now so that you can go ahead and get your work done. Hopefully you're having a good day, and I hope to see you again soon. Bye now.